Okay, let's solve the problem A from today's contest. And we're given a k and a set of all integers from L to R inclusive. And we can do the following operation. We will choose an x from the set such that there are at least k multiples of x in S. And after that, we'll remove x. And we're asked to find the maximum possible number of operations that can be performed. So how should we remove the values that we can perform maximum number of operations? So for the first test case, we're given 3, 9, and 2. So we have 3. So the set S is 3, 4, 5, 6, 7, 8, and 9. So let's try to remove 3. For 3, the reason we're removing from smallest to largest is because removing a smaller value will not affect the further operations. In the future, if we want to remove, for example, a value, let's say 4, so the smaller value will not affect this. We're not removing any multiple of 4 if we remove smaller values that are smaller values from 4. So we have 4. So for this first operation, we have 3. How many multiples we have? We have 3 itself, and we have 6 and 9. So we have 3 multiples, so which is greater than 2. So we can remove 3, and then move on to 4. For 4, we have 4 itself and 8, and 2 is greater than or equal to 2. So 4 is also removed, and we have 5. For 5, we have only 5. So 1 is less than 2. So for 5, it's not possible. So is it rational to move on to check other values? It's not actually, because for 6 or 7 or 8, any value larger than 6 will larger than 5 actually will not have their multiples more than 2 or equal to 2. So for example, for 6 there's only 1. For example, for 7 there's only 1, and for 8 there's only 1. So I have done a binary search over the given range to find the last value that is for which this operation is possible, removal is possible. And for this sequence, it's 4. So we can do one by one, but this will probably give TLE. And so yeah, we find 4. So from 3 to 4, I guess, yeah, from 3 to 4 we remove 2 values. So you can do binary search. So if you want to see the code, so that's what I did. So I did a binary search over the given range, and if it is possible that there is no value that we can remove from the given set. In this case, we'll set 0, otherwise we'll report the answer. Now actually, let's move to B. In B, we're given a string of length n, a binary string of length n, and another string r of length n minus 1. It's also a binary string. And we're playing a game, and during the game, we'll perform n minus 1 operations on S. In the ith operation, we'll choose some k. We'll choose some k such that S, so this is the given string, sk is different than sk plus 1. And afterwards, we remove sk plus 1. We'll replace sk plus 1 with the current value in the r, the other string. So basically we remove a pair 0 1 or 1 0 every time. For example, we're given 1 and 1, so we'll do only one operation, and the first operation, the value that will replace such a pair is 0. So but we do not have 0 1 or 1 0 here, so for this test case it's not possible. So we have 0 1. These are rather trivial. We have 0 1 and we're given 1. We can replace this by 1. So where it's possible to do all of the m-1 operation. So the answer is going to be no if we cannot do all of the m-1 operations. Otherwise, it will be yes. So for the third test case, we have 1, 1, 0, 1. Let's see, 1, 1, 0, 1. And we have 0, 0, 1. So the first time we're given 0. That means we'll replace a pair 0, 1 by 0. So what do you notice here? When we replace a pair 0, 1, so every time we're replacing a pair 0, 1 or 1, 0, it doesn't really matter. So we replace a pair with 0, 1 with 0, then the number of zeros does not change, but the number of ones decreases. So if we have, well, let's say these are ones, and after that we have zeros, and these are ones. And for this pair here, if we replace it by, so this pair, if this gets replaced by a 0, so then basically the number of zeros does not change. So let's say this pair 1, 0 is replaced by 0. So we have 0, 1, 2, 3, 4 zeros, and the number of ones decreases. So every time, so this is the idea, when you replace a pair 1, 0 with 0, the number of ones decreases. So let's say ones, so this decreases. Otherwise, if we replace it with 1, the number of zeros decreases. So in order to do the operation, we should have at least one pair 1, 0 or 0, 1, so we can do the operation. So idea is clear. Let's see another test case. For example, this one here. Okay, we have 1, 1, 1, 1, and 0. Let's say, I don't know, what was it? Like 0, 0, and 0. In the first operation, we'll replace a 1, 0 or 0, 1 with a 1. So that means we'll decrease, in the first operation, we'll decrease the number of zeros. Now, first of all, do we have 1, 0 or 0, 1, at least such a pair? So in order to know that, we can check if the number of zeros positive and the number of ones positive. That means if there's at least 1, 0 and at least 1, 1, then there is a pair 0, 1. So we can do the operation. So once we check this, we can do the operation. So 1, 0, so we're replacing the 1, 0 or 0, 1 with a 1. So we're decreasing the number of zeros. So we say, okay, zeros minus minus. So basically we're decreasing it. And in this case, we replace this here with a 1. So basically we remove this 0 here. And now we have this. So in this case we have 4 ones, but we don't have any 0. So in the next operation we won't be even able to do the operation because we don't have 1, 0 or 0, 1 pair. So for this the answer will be no. And let's see for the last test case here. It's all a bit quite lengthy. 1, 0, 0, 1, 0, 0, 1, 0. Okay. 1, 0, 0, 0, 1, 0. What was the other one? Okay. Well, now we have 3 ones. Let's just keep track of them. Like this is 1, this is 0 as a counter. We have 3 ones and we have 5 zeros. First time we replace a pair with 0. That means we're decreasing the number of ones. Okay, do we have such a pair? Yes, we have, because we have at least 1, 1 and at least 1, 0. So we decrease the number of ones by 1. So now we have 2. The next one also is 0. Now we have 1. Then we have 1. So we're decreasing the number of zeros. So now we have 4. So then we have a 0. So we're decreasing the number of zeros. So number of ones. And now we have 4 and 0. And then we have, again, a 0. So for this 0, we don't have a pair. We actually, I haven't done the real operations on the string itself, but you can, I believe there is a way to end up with 4 zeros and no ones if you perform this way, and then you'll fail to do the operation, this operation, because we don't have 1 0 or 0 1 pair. So basically we'll keep track of zeros and ones, and every time we have a 0, this decreases the number of ones, and every time we have a 1, this decreases the number of zeros. I wasted quite a lot of time on this problem by misleading the statement. I thought that I'm going to replace sk plus 1 with rk, and I mean, I thought all sort of stuff, and yeah. Okay, now let's go here. Okay, this is the code. Okay, I read in S and R and count ones and zeros, and then if we have a 0, and we first check if we have a pair, a valid pair, and if that is the case, since this is 0, we're decreasing the number of ones, and this case is similar for 1. If we have 1, we're decreasing the number of zeros. If it is not possible in any of these cases, we'll just say, okay, this is not possible, just break here, and at the end we'll check if we can do all the operations. If yes, then we'll print yes, otherwise no. Yeah, that's all. I wasn't able to solve C. Probably this is a lot harder, I believe. So, but I'll try to solve after the contest, and if needed, I'll post the solution and explanation.